Uh, so, example one. In example one, we have a beaker of water and it is accelerated towards right. Then the question is to locate the image I. Okay, the object is placed beneath this beaker. So when I accelerate towards my right, this becomes slant. Uh, to locate the image, we need at least two rays. And we choose two rays. The first ray we choose is the ray that will be perpendicular to the surface. The reason is it won't deviate. So look, this is the ray I drew perpendicular to the surface from the object. And the second one is an arbitrary one. You will just choose a random. So here I have chosen this, and this is the normal to the surface. As it is going from water to air, it will deviate away from the normal and just extend it behind to find where these two light rays intersect. And that is the place the image is going to form. And I is located. So I have mentioned the procedure here. Example 2, we already have given the location of the image. And now they have given an additional uh, light ray. Let's say that's OA. And the question is to complete. So this is OA. Complete the ray OA. Complete the ray OA. So how we can do this? So I'll mention the idea. OA contributes to form image I. Therefore, therefore, draw the ray. Therefore, draw the ray from I. So just draw this ray from I. Here dotted line and here solid line. So this has to be the direction of ray, or this is the refracted ray. Okay. Hope the idea is clear. So the next topic, real depth and the apparent depth. Real depth and apparent depth. Yeah, done. So again, we have the same diagram. We have the object right here. Uh, what is the real depth? Real depth is the real thickness of this block. This is the real depth. Let's take it as H naught or H object, HO. But when you look from above, do you see the object or do you see the image? You actually observe the image only. So image is observed at a certain distance, HI. Okay, so here, now it is actually located at a certain distance, HI. So uh, actually the height is H naught. So that's the real depth. And what we observe is HI. So that's the apparent depth. Now we are trying to get a relationship between HI and H naught. So here we have two rays. One of the ray is perpendicular, therefore no refraction. And the other one is not perpendicular, so there is a refraction. Now let's say this makes an angle alpha. So alternative angles, this is also alpha. And let's say this angle over here is beta. Then this angle is also beta. Again, it's the corresponding angle. So when we have two parallel lines, these two angles are alternate. And when we have two parallel lines, these two angles are corresponding. So alpha is alternate angles and beta is corresponding angles. So let's apply Snell law right here. If I apply Snell's law right here, Snell's law, we have in, I'll consider this one as medium 1. Okay. I'll consider this one as N1 and this one as N2 to be more general. So if I apply Snell's law, it is going to be N2 sine alpha that is equal N1 sine beta. But what we're going to do is we're only going to use this equation when we look from right above, okay, upright, not for different angles. So what we can do is we can consider small angles for alpha, okay. We are only going to consider small angles for alpha. So although I have drawn the diagram for a larger angle, we can change it, right? So when we change it to small angle, in small angles, there is a special relationship. For small angles, for small angles, sine theta is almost equal to tan theta. So due to that reason, I can replace N2 tan alpha is equal N1 tan beta. Now, what is tan alpha? Tan alpha is opposite over adjacent. So let's consider this opposite distance as x. So opposite is N2 tan alpha, that is going to be opposite is x over height, that is h naught, is equal N1. And for tan beta, we have opposite is x and adjacent is hi. X over hi. So x gets cancelled and we have n1 over n2 let's take n2 over n1, that is equal h0 over hi. So this one could be written as, we can write this one as n2 respective to n1, n2 respective to n1, that is equal h0 over hi. That's equal to h0 over hi. So h0 is the real depth. This is the real depth and this is the apparent. Okay, is the derivation clear? Let's write this in a separate equation. So n2 over n1 is equal real depth over apparent depth. Once you have completed, let me know. So here, there are a few conditions that we have to remember. So we made an assumption, right? The assumption is this is only true for small angles. So if this is true for small angles, uh, this I has to be always placed upright to this object, not at any other angle. Okay, so not number one, not number one. The first thing is the equation is valid. The equation is valid only when I is placed upright upright to the object. Okay, because one of the light ray we considered is also perpendicular, which is only possible if we place it upright. And the second, if you look at the equation, we have n2 respect to n1. So that is the equation or the refractive index. The refractive index n is used of the medium n is taken with respect to where the I is placed. Where the I is placed. Because we have placed in medium n1, we are getting n2 respect to n1. Okay, so we always have to use with respect to the medium where the I is placed. Let's look an example. So example 1, the eye is placed in air and this is water. The refractive index of water is equal NW is equal to 4 by 3. Okay, and the real depth to the object is 12 centimeter. Then what you have to do is you have to find what's the apparent depth. So actually both of them should be in the same line, but if we draw it in the same line, it's hard to do the calculation, right? That is why there's a gap between them. Okay, don't misunderstand that. So what we have to do is we have to find x. So here we are going to apply n of water with respect to air. That is equal real depth, real over apparent, real over apparent. So NWA, that is 4 by 3, and the real depth is 12, and the apparent depth is x. So simplify for x, you get x is equal to 9 centimeters. So if I'm done with the first, try the second. So this is water and this is glass. The refractive index of water is 4 by 3 and the glass is 3 by 2. And the real depth is 18 centimeter. And you have to find what is x. Done with the first. Okay, I'll do it on the screen. You try by yourself and then check the answer. You get this answer. Example 3. So this is a bird which is at a height of 18 centimeter, and this is a fish which is at a depth of 16 centimeter. The refractive index of air is 1, refractive index of water is 4 by 3, and the question is the distance. First one, distance to the fish from bird. Second is the distance from bird to fish. Again, it's the same question. From fish to bird. Okay, I'll use the same sentence pattern. Distance to the bird from fish as observed. Not the real, but how they observe each other. So first what you have to do is you have to find out at what is the real depth, what is the apparent depth for bird, and what is the real depth. Yeah, in the second one, what they have done is they have given the absolute value. Absolute value NW is 3 by 2. And in, sorry, in glass is 3 by 2. NW is 4 by 3. So you have to find what is GNW with respect to water, because they have given with respect to air. If they have given NGW straightforward, you will use the given value straightforward, which is equal to 8 by 9. Okay, Imla. Here you had to find it first. So you have to be very careful about the information they have given. Or have they already given with respect to, or is it different? So here what you have to do is first you have to find what is the apparent depth the bird observes. So I'll do the first question. So the first one, distance to the fish from bird. So first let's see at what depth does this bird observe the fish. So I'll consider it as X. So bird is watching from air. Then we have to write NW respect to air. That is equal real over apparent. So real is 16, apparent is X. That is equal 4 by 3. So by calculating, we have X is equal to 12 centimeter. Now, from the surface of the water, it sees at a depth of 12 centimeter. And already it is at a depth, height of 18 centimeter from water. Okay, so this is the image. Therefore, distance 1 is equal to 30 centimeter. Did you get that idea? Okay, try the second one. Got this answer. So did you observe something interesting? When we look from rare medium, when we look from rare medium into dense medium, the image looks closer. But when we look from dense medium into rare medium, the image goes further. Okay, so maybe we can include it as a special note too, because these types of small informations, they will be helpful for MCQs. Distance, apparent distance increase. No, apparent distance reduce when looked from rare medium into dense medium, and it is the opposite. Oh, and apparent distance increases when looked from dense to rare, dense into rare medium. Okay, done. Next topic. Next, we have an experiment using this apparent depth and real depth. We can find the refractive index of a glass block. So the topic is determination of refractive index of a glass block using traveling microscope. Let's say this is the glass block. And we place, so what do we need to find? We have to find the refractive index n, which is equal to real depth over apparent depth. So somehow, if I can find the real depth and the apparent depth, then I can find what is n. To do that, what we have to do is we place an object on a piece of paper. We take a piece of paper and put a cross mark and place it beneath. And when you look, you have placed the paper beneath. Okay, first you do not place the glass block. Just placing this, you will take the microscope reading RA. Okay, so this is the first thing you have to do. That is RA. And next, next you place this sheet of paper on top and take RB. So how to take RB? Now you have already adjusted the microscope. Now this microscope will focus only this distance. Okay. Microscope will focus only this distance. So when you are close, now let's say this is the same case, okay? You didn't move. This is RA. Then when you look through the microscope, will this image be clear? No, it won't be clear. To make it clear, what you have to do? You have to move this telescope behind, somewhere here. That is RB. Now it will be clear. So this distance H, or this distance, let's say X. How can we find X? X is equal RB minus RA, or the difference between RB and RA. Okay, so I'll tell that's the modulus of RA minus RB. Did you get that idea? Similarly, now we have placed it on top, right? Again, we'll place it bottom, beneath. And now, when you look through the telescope, what are you going to observe? Will you observe this cross, or will we observe this image? What are we going to observe? We are going to observe the image. So you will have to move the telescope slightly down to focus it again, somewhere here in between. So let's take that reading as RC. Now, this is the distance I need, that is Y. So how to get Y? This distance is going to be Y, right? So Y is equal the difference between RB and RC. So now we have found the real depth, and this is the apparent depth. Using those two, I can find the refractive index. So the experiment in simple. Are you clear with the idea? Next, we can write it once again with a proper note. For now, are you clear with the idea? How are we going to conduct the experiment? Okay, the meeting might end now. I'll give the note in the next one. Wait for 2 minutes until it gets saved.